Wonderful. Thank you very much. Thank you everyone it's such a great pleasure to be back here at SD&A. My talk is going to be different because, well, I'm from the industry. I don't come from academia, so the presentation is going to be more about applications and actually one that is very, very close to my heart, which is how to take historic stereographs and bring them back to life. Now, historic stereographs, they've been around, like it says, for a very long time. So the golden age, the first real golden age of 3D, for those who don't know, was between 1830 and 1930. And honestly, it was between 1850 to 1920. That was really when 3D was everywhere. And this is an actual very accurate picture of somebody in the Victorian era watching a 3D picture in the home. So there's an incredible heritage of these pictures. There are literally millions of these 3D pictures, places that do not exist anymore, places that have since been destroyed, and key figures like Abraham Lincoln. We have pictures from the Civil War. We have pictures from many historical events. Now the challenge has been, and on top of that, there's a lot of pictures that were made by individuals who had 3D cameras. So these exist out there, but they mainly remain in the realm of people collecting them and viewing them on their stereoscopes. And I had the opportunity to meet one of these collections. Well, that one is a public collection from France, an organization called CLEM Patrimoine. And these guys have access to, well, their collection right now is at about 25,000 pictures. And we talked and we decided, well, it's a shame. We should bring them back. We should make them available to any kind of display. So we set out on a project to actually achieve that. So there were 4 key requirements for that project. The first one is it had to work with digitized sources. Basically, all these collections have scanned their pictures. They're already out there, and well, they don't want to redo the entire work, and I totally get that. I totally accept that. So we had to start from these scanned pictures. The second one is to minimize the archiving storage space, and this is a priority for Archéovision. And Archéovision is part of the National Research Council in France, and they want to limit the footprint. They want the carbon footprint of these things, and they don't want to be too heavy. Third one was compatibility with regular displays. So yeah, we have to go full out anaglyph for this because it's not enough to just go to a handful of 3D devices out there. And lastly, and that's where I stretch myself out, is the adaptation has to be automatic. So what that means is we don't want any user to come in and say, oh, I have to do this, I have to do that, oh, it's uncomfortable for me, I have to play around and zing around with the sliders and all that. It has to be 100% automatic. So at first I thought, yeah, it should be a slam dunk, not too bad. Yeah, we're pretty much standardized. And, well, boy, was I ever wrong. This was probably the toughest project I ever started with. So let's start with the content issues. One is the various size of images. So I thought I've always been exposed to only a single type of stereographs, but actually there are 5 major different categories, millions out there, on glass plates, on cardboard, on even daguerreotypes and whatnot. There are many different types, and they all have different size of images. So you cannot just go out and standardize one way to process for all images. On top of that, sometimes on glass plates, they vary sizes on these plates. Worse than that, the left side image and the right side image are not even the same size. So once you try to make something that's standardized, well, you work with something that is absolutely not standardized. Then the framing issues, top right, dramatization of a scan, but you can see that the images, the scan is crooked, the images on these are crooked as well. So this is really a problem if you want to have a standard process for everything. The misalignment of images is pretty obvious at the bottom right. So at the bottom right, see these images? They are very clean. Trust me, this is a clean one. Some of them are horrible. So this is like very well framed, right? Left and right, very well framed, side by side. All looks good, except that if you look at the green line and the yellow dots and the red dots, you can see that they're misaligned horizontally. Very common. These pictures, these people did not care. They just slice them, put them on a cardboard, and try and enjoy it, right? Left and right inversions, very common. Even left, right. The very, very common things. Extremely varying disparities. So there was not one technique to shoot 3D at that time, and techniques evolved greatly. I had a great pleasure of working with Denis Pellerin. He's one of the world's authority in historic stereo pictures, and telling me how they were shooting them. And in some of the pictures, they were taking them like first picture, second picture, like the cha-cha method for those who are familiar with that. But they were taking two pictures, not synchronized, and people would move, and you can see some very weird things happening in these pictures. But this is very common. So sometimes the disparities, they can go from many centimeters to sometimes just a few millimeters in a picture. So no standard there again. And finally, changing cropping techniques. So later on, they've realized that it's better if the first or the closest object is at the frame of the picture. It's actually at the same distance to the frame of the picture. So the closest object should not pop out, if you want, of there's no negative parallax from if you superimpose these pictures. But guess what? Look at this picture. The closest object is a basket. That basket is popping out like crazy from the frame. So once again, no standard anywhere. So anyways, in order to develop a method that was robust, we had to face all these different issues. And then there are display issues. I won't go through that too much in detail, but the screen size information is not reliable. So if we want to do something that's automated, we need to figure out what's the size of the screen. It turns out that whenever you get information back from the display, it's not all that good. Even if there are standards, people are pretty liberal with their respect of the standards. There are framing issues, because if you don't show the pictures one on top of the other, then there are different parts on the left and the right, and that really is annoying for the viewing and the comfort, and then ghosting. So what did we do? We set out to say, okay, we cannot do a one-size-fits-all approach, so we will have to adapt for every single picture. So in order to do this, we do it as a three-step process. The first step is image analysis. So we look at the picture and we try to determine key characteristics of the image in order to be able to do the processing. Then we establish the safe viewing parameters, and we optimize the anaglyph output. The steps 2 and 3, they're done in the player, in the CubicSpace volumetric converter. So that's where it's done. And step 1 is done before to archive some information. So that tool was developed with Archéovision in France. So it's a semi-automatic tool. So basically what it does, it will help the user figure out where's the left image, where's the right image. This is a pretty clean one, but trust me, there are some images that are absolutely horrible, and you do not know when it starts and it ends with the rest of the medium. So we identify the left and right image, the bottom left and bottom right for alignment purposes. We also determine the respective coordinates of the farthest and closest object. So here you can see, well, they're very, very small, but you can see like wait a minute, there you go, the red dot here and the green dot here, red dot here, green dot here. So these are the closest and farthest objects you can see in that scene. Obviously, this is semi-automatic. This was for the project. Now that we know it works, obviously, we're going to be starting to do some fully automated identifications of these points. using disparity maps and depth maps. So anyways, so by doing that, we store key information in the picture, and we store that information in an SVG file. Now, SVG files are very, very lightweight, very common, very standardized, and we can put that together on a data bank next to the picture, and it's extremely efficient to distribute and to do our processing. So once that is done, we have a picture, we have the SVG file, they are stored together, then we start the processing. So in step 2, we determine the safe viewing parameters. We determine, this is part of a project that we've done before and with the CubicSpace technologies to determine what is the maximum depth plane and the minimum depth plane that it will be comfortable for a given user and a given display and the distance to that display. So there are certain disparities that will be okay if you have a screen that's close to you, if a screen is more distance. If you're a kid, your eyes are going to be much closer, your IPD is different. So we wanted to adapt that to make sure that we would be comfortable in all the different conditions. And then we're able to determine what's a maximum magnification that we can allow for any given picture. And once that is done, then we generate the anaglyph output. So the first thing that we realized is that we needed to do an initial calibration. As I said, the size of the screens are not really good. The information is not reliable. So what did we do? Well, we decided, okay, let's put a picture of a credit card on that screen and let people slide, because we tried to find one object that is pretty common everywhere in the world and that everybody can use and will be the same size. And that turned out to be pretty good. Now, some people said, yeah, but people will think that you're going to rob them for their credit card. It's like, oh, come on. Maybe, but anyways, that's the solution that we found. And it works really, really well to do a calibration for the size. So people just put their credit card on top and just match the sizes. And then we have a reliable display size information. And then we also calibrate for crosstalk. So that one is not highly scientific. We just put the glasses on top of it, and we have a little slider, and it can, and when the ghosting disappears or is the smallest, then that's where it stops, and then it is set. We have an anti-ghosting algorithm that we run. So once that is done, so why we call it a volumetric converter is because the way that we do it is we place in 3D space in an OpenGL environment. We put a geometry. It's very similar to what is being done in VR video. So we create a geometry, we slap the texture on it, which is the actual picture, the information from the left eye picture and the right eye picture. We place a camera dead center, and then we can play with the field of view and the shifting of the camera to generate the comfortable viewing with a maximum depth, maximum disparity, and minimum disparity to have a comfortable experience. So one thing that's interesting here is that we can determine a zooming factor. So we are not forced to stay at the level of the, or at the original zooming or. So what we try to do is the first picture that we generate on the screen is full screen in height. So that's what we do. So that's what we target. If that magnification is too big to be comfortable, we stick to the smaller version, which is the maximum zoom that you can do. And if not, we fill in the screen, and then we allow a zoom in and a zoom out of the picture. So that's actually the super killer feature, like people love it. So you can actually explore the images in real time. So you have the picture, you just pinch zoom in, out, move around. Of course, you're wearing anaglyph glasses. Oh, well, there you go. I'll show you the tablet afterwards, but there you go. And you can zoom in and out of these pictures, and you get a really comfortable and very enjoyable ghost-free experience. So basically, yes, we have successfully developed a universal method that takes, first it needs, it's adapted to all types of stereograph cards, whether it's glass, cardboard, whatever, anything that's been created whenever, we can do it. It uses a regular regular scans in simple SVG files, so it's robust and lightweight. We can provide automatic adaptation to viewing conditions, and it's easily portable to devices and browsers, so we can do it on any Chrome browser or any device whatsoever. I do it on my iPhone. I have a website. We can put it on the laptop or whatever, and it works great. We can blow it up to this screen, or we could use it all the way down to a phone. So that's it for me. Hey, I'm over by 25 seconds. Okay, that's on time. Thank you very much, everyone.